We discussed the Jordan-Hölder theorem for finite groups. So suppose we have a finite group G, then it has a sort of decomposition series where the subgroups H are normal with respect to the next subgroup, and this composition series ends when we reach the group G. And the series has the property that if we divide hi plus 1 in this series by hi, then this is a simple group. And this simple group is called the composition factor of the composition series. And the statement of the Jordan-Hölder theorem is that these composition factors are the same for any possible composition series. So that is up to permutation. And the number of groups that appear in this composition series is always equal. That's the theorem. And how do we go about proving it? Well, the first observation is that we can pick H, for instance, k minus 1, maximal normal subgroup of G, which you remember was HK. Then the first thing to notice is that HK over HK minus 1 is indeed simple. And this is a consequence of the third isomorphism theorem, which also says that that the normal subgroups containing HK minus 1 are in one-to-one correspondence with the normal subgroups of the quotient. And therefore, because HK minus 1 is supposed to be maximal, there are no longer any normal subgroups, and therefore HK over HK minus 1 is simple. So each time HI is a maximal proper subgroup of HI plus 1. All right, so now we still have to prove that the composition factors are the same and that K is an invariant. So we perform the proof of the Jordan-Hölder theorem, and the proof is by induction on the cardinal number of the group G. So we suppose it's valid for smaller groups G. Obviously, it's valid for the trivial group. Let's suppose now that we have two composition series of the group G, which are HI running up to HK and KJ running up to KL. So these series, they end by HK minus 1, which is a normal subgroup of HK, which is G, as well as KL minus 1, which is a normal subgroup of KL, which is again equal to G. So then we have groups HK minus 1, which is equal to H, we'll call equal to H, and KL minus 1, which we will call K. Now, if H is K, then it is easy to see that we are done. And if H is different from K, then we'll work with the group which is the intersection of H and K, which is clearly also a normal subgroup in G, as well as in H, as well as in K. Now, H intersection K is clearly smaller than G, and so the induction hypothesis is valid for H intersection K, And we can suppose that it has a composition series which is given by Lm running all the way up to, let's say, T. Now we note that for H we already have two composition series. We have H, I, all the way up to k minus 1. And then we have the composition series of L, which ends with L t minus 1, which sits in LT, which is nothing but L itself, and then that sits in H. And the claim is that these are two composition series for H. Now, why is this? Why is L maximal a maximal proper subgroup of H? Well, this is by the second isomorphism theorem, which says that H divided by H intersection K is equivalent to G over K. And since K is a maximal normal subgroup of G, H intersection K is a maximal proper subgroup which is normal in H. So therefore L is indeed a maximal normal subgroup in H, and we have indeed two composition series. So this implies immediately that T is k minus 1. Now clearly we can repeat this reasoning by replacing H and K, and we will find, since we work with the same group L, that T is now L minus 1, and therefore from these two we immediately have that K is L. Moreover, we have that the H series is equivalent up to the last two entries with the L series, which is equivalent with the K series, equivalent meaning in the sense of the properties of the Jordan-Hölder theorem. And because this is the case up to the last two entries, we already have that all of these quotients are equal up to permutation, except for the last two entries. So what are these? We have the L series, and then we have either H and then G, or we have the L series and then K and then G. But we've already established that H over L is nothing but G over K, while K over L is nothing but G over H. And so therefore, if we look at the last two composition factors, then for the upper series, they are G over H and G over K. And for the lower one, they are G over K and G over H. And therefore, since the rest of these series are already equivalent and the last two are as well up to permutation, we indeed get the Jordan-Hölder theorem proven.